Okay, so you spent yesterday in your homework. Listen carefully. You really need to listen to this because I said the same thing to my class this morning, and then at the very end they were still kind of confused. So hear my words. You spent part of the work yesterday, part of the practice, completing a table of values so that you could get some points. And that's a good thing to be able to do, to be able to sub it and solve anyway. Like, that's a good skill. And I hope you got some sense of the patterns in parabolas as you did that. And today we're going to, as you can see, if you look at the note, we're going to do a little bit of sort of table of value stuff. However, none of your homework should be done with a table of values. Okay, unless we're doing it in a lesson, you will no longer be graphing with a table of values. Does everybody understand me about that? Like, that is not how we're going to do this. In fact, what we're trying to learn today, we're going to notice two things. And those are going to help us graph without a table of values. Do you remember in grade 9, when you first started looking at linear relationships, how did you graph them? With a table of values. And you picked your x's, you subbed them into the equation, found the y's, had 5 points, and connect them with a straight line. Do you remember doing that? Sort of? You don't? Okay. Anyway, you probably did that at some point. But then you learn about y equals mx plus b. And you don't use table of values anymore. You just plot the y-intercept and use the slope to find more points. Do you remember doing that? Oh, jeez, killing me. Okay. So anyway, but you did that. We did that this year when we did a little bit of graphing here or there. You graph with y equals mx plus b, not with a table of values. That's what we're going for with quadratics and parabolas, is graphing without a table of values. Table of values is slow, cumbersome, takes up a lot of space, is not a good way to do it, and it doesn't help us understand the relationship. So, as I said yesterday, parabolas are much more complex shapes than linear relations, so there's more to them, and it takes a little bit longer to learn all of those specifics so that we can graph quickly, like with y equals mx plus b. So we do it over a few days. It takes a little bit more effort, but that's what we're doing. Okay, so have that goal in mind. By the end of this period, you should know how to graph certain kinds of these quadratics without a table of values. That's what you're aiming for. Does everybody understand that? Is that clear? Some people daydreaming and they weren't listening, and they're going to ask me, what values do I use in my table at the end of this? Because that's what's going to happen. Okay, anyway. Take a look, a quick note at the very top. One thing we did talk about yesterday is the parabola, is what we were looking at, and the properties of the parabola. But really what this is kind of a picky distinction, but what this unit is about quadratics. So a quadratic relationship is a different kind of relationship from a linear, and there's lots of other kinds. So linear in grade 9, quadratic in grade 10, and the graph of a quadratic we call a parabola. Okay? But we're looking at quadratic relationships. What makes something a quadratic relationship is when it's simplified. And take a look at these 3 examples here. They all have an x squared part to them. Do you see that? If I flip to the next page, you see that there's a squared over the brackets, but that's still like an x squared. So once in a while, it's sort of hidden, but quadratics always have that x squared at least hidden in there somewhere. That's what makes it quadratic. So we'll come back to this later, but that's something you're supposed to know, that if you look at an equation, you can tell that it's quadratic. Okay, that's one thing you're supposed to know. So just that's a big part of what we're doing. Okay, the biggest exponent on the x is a 2, then it's a quadratic relationship. If you only had a 1 on the x, it would be linear. That's what you do in grade 9. Y equals x. X to the 1, that's linear. This is y equals x to the 2. That's quadratic. Okay, that's the difference when you look at the equation. Okay, all right, so let's get to it. So we are going to kind of use the table of values here, but that's not what we're aiming for by the end of this. Okay? All right, so here's the x's that we're going to use. Whoops, I don't want green. negative 3, negative 2, negative 1, 0, 1, 2, and 3. And we did this yesterday, and hopefully you're starting to get kind of familiar with this pattern. I square negative 3, I get 9. Square negative 2, I get 4. Square negative 1, I get 1. And in fact, this is a pattern that you would do well to basically memorize. I mean, it's easy to just square the numbers, but understand that those 7 pairs of numbers are important starting points for what we're trying to do. So this graph here, this graph here, y equals x squared, is what we call the base function, or the parent function, or the parent graph of the quadratic. It's just basic, nothing fancy, no extra numbers. You look at the other equations on the page, there's more numbers, right? And so everything we're going to do over the next few days, we compare to this base function, to the base graph. And the base graph looks like this. If we graph it, negative 3 and 9, negative 2 and 4, negative 1, 1, 0, 0, 1, 1. So already, it would be great if you thought you could graph that without writing down the values, without a table of values. Just kind of know, the vertex is at 0, 0, and then I go over 1, square it, up 1, over 2, square it, up 4, over 3, square it, up 9, and kind of just build the points. Even if you did it in your head as you went, that would be okay. But without writing out a table of values, if you could graph that one, just straight up, that's a good start. Understanding that relationship. Okay, whenever, the rule of thumb is whenever you have more than one relationship, one curve or line on a graph, you have to label them. So we'll do this. We'll call it 1, and over here I'll call it 1, y equals x squared. The equation of that guy. Does that make sense? Everybody good so far? Pretty straightforward. Now let's do the next one, x squared plus 3. So there's 2 ways you could think about this. I could do the whole BEDMAS thing where I sub in negative 3 and I square it to get 9, and then I add 3 and get 12. But I can also realize that the second column there is x squared, and I'm just adding 3 to that, right? To get my y value, I'm actually just taking this, because that's the x squared, and adding 3 more, because that's what my equation says, add 3. Okay, so then I can do negative 2 squared, which is 4, and then 4 plus 3 is 7. 1 plus 3 is 4, 0 plus 3 is 3. And then again, the same pattern, look at how they repeat. That's like something that you want to be getting familiar with. Mahmoud, you had your hand up? Question?
No, I was just stating the similarity stuff of formulas.
Nice. Okay, good. That's good. That's the kind of stuff you want to look at, is those patterns. We're gonna graph all 3 of these and then talk about it. So what if I plot these points? Well, just watch for a minute. Look what I did. I went to 9, but then I added 3, so I got 3 more. Then I went to 4 and added 3, got 3 more. Went to 1, added 3, got 3 more. 0, added 3. And then they repeated like that. So there's my 7 points. Notice that I graphed them in red. If you have other colors, it might make your graph easier to read if you look back at it later, to use another colored pen. And we'll call that 2. All right. And what's the last one? We go back to column 2, x squared, but now we're subtracting 4 from it. X squared minus 4. Everybody with me? So 9 minus 4 is 5. 4 minus 4 is 0. Negative 3, negative 4, negative 3, 0, and 5. like again, if you felt like that's going too fast, like you're not really seeing where I'm getting those numbers, that's okay. Like we're not doing a table of values anyway. That's not how we're doing this. The whole point of this is to notice something else, because we're not graphing with the table of values anymore. So once we notice that, we will no longer be writing out all these values. So don't worry too much about that. Yes?
How do you get the x values in the restart though?
I just made them up. This is just part of the lesson. Yep.
For that?
No, we're not doing table of values. So you don't need x values, right? There's no table of values, so that nothing, you won't be given them because you don't need them. Okay, let's graph these guys. -3 and 5. -2, 0, and 3, 5, and 2, 0, and there. So we'll call this guy 3 in blue. And there we have it. So here's the trick. Does anybody notice anything about what happened between those three curves? Anything?
If you add a number to the x squared, it goes, if the vertex goes up, if you subtract a number, the vertex goes down.
Very nice. So I added 3. How much did the vertex go up? By 3. That's convenient. I added 3 at the end. Vertex went up 3. What else went up 3? Riley? Every other point. Take a look. If I take this and I move it up 3, every one of these points, see the red points where it started? Can you see these? The red points where it started, it moved up 3. The red point was where it started, moved up 3. Red point was where it started, moved up 3. What happens if I moved it down 4? Same thing. These red points all moved down 4. So did the vertex. So did this point. So did that point. They all moved down 4. You can see it on the graph. The vertex moved down 4, and every other point from the original black curve moved down 4. Yes?
So will all the parabola equations be y equals mx plus b, or?
It's not mx plus b, no, because that's a linear relation. But we're going to get that kind of a general form by the time we're finished this, like Friday. Okay? You notice it says up here, y, I didn't talk about this yet, but y equals x squared plus k. So k is the value that moves that graph up or down. If k was 5 plus 5, I take my parabola and move it up 5. If k was -10, it'd be x squared minus 10. I take my graph and move it down 10. That make sense? Okay. Every point moves together, so you notice that the shape of the graph doesn't change. Right? If this is my parabola, it just moves up, down, but it doesn't warp the shape at all. It keeps the exact same shape. And this is a bit of a tricky question, but it's a good thinking question. What one of those properties that we talked about yesterday defines the shape of the parabola?
X squared?
Yes, that's not one of the properties though, but you're right. You're absolutely right. That is what it is. The growth pattern defines the shape. This didn't change the growth pattern. Go to the vertex. From that vertex, I go over 1 up 1, over 2 up 4, over 3 up 9. Same growth pattern. So same shape. I just moved it up and down. Okay. Let's take a look at some of the properties. What was the domain of x squared, Jaden?
Brackets, x is the element of the
And what does that mean? That's perfect. X is an element of the real numbers. But what does that mean in natural language? Go ahead.
x can be anything.
X can be anything. Any value of x on that grid will work. Awesome. Did that change when our graph became x squared plus 3? Liam, no? Good. So it's still x is an element of the real numbers. And what about when I did x squared minus 4? What's the new domain there? Same thing. What about range? What's the range of the black curve, the first curve? You can tell me with that notation or just natural language, it's fine.
X is an element of real numbers along with y is equal or greater than -4.
Still there? Fine. It's Mr. Dollar. Yes. Yes. In the main office. That's lean back to the office. No. Okay, so the range was y is an element of the real numbers such that, I think you said this, but y is greater than or equal to 0. So y could be anything 0 and up. Did that change for x squared plus 3? Owen, what do you think? So y is an element of the real numbers such that, did that change? Very nice. Nicely said. So in other words, y is greater than or equal to 3. So it did change. So the plus 3 changed the range, did not change the domain. Thinking about how this changes the look of the parabola and the properties of the function that we list like this, that's part of how you'll get a sense of what the relationship is like and how the equation works. Okay, and what about that last one? Jaden, what do you think?
Y making this long, such as it's greater or equal to.
Nice. Okay, good. Vertex of the first one was 0, 0. The x's didn't change, it just moved straight up, so it's still 0, but of course the y moved to 3. And that matches with the range. And then same thing here, the x's didn't move, but the y moved to -4, so matches the range. Axis of symmetry, again, the x didn't change. So what is it here? It's x equals 0, still x equals 0, still x equals 0. And then the optimal value, is it a maximum or a minimum? Some people think it's a maximum because the arms both go up and they like go maximizing to the sky and they go on forever, and that makes it really big, so that's like maximum, but that's wrong. That's not what we mean by max or min. Megan? It's a minimum because there is a value that is the minimum value that it'll never go below, just like what the range is saying. So minimum of 0, this always matches the range, minimum of 3, and minimum of -4. It didn't change whether it was a minimum or a maximum, but it did change the value. Okay? Some things to think about. Yes?
When did it put the maximum?
When it has a maximum, it would look like that. Okay? We're going to look at that a little bit more tomorrow, but there were a few in the work yesterday that had that, and just when it's opening downwards, it has a value that's maximum that it'll never go above, right? Yes?
The domain and range always be some form of that.
They always start, for us, they always start x as an element of the real numbers. And then if there's a condition, like for the range, such that y can only be things 0 and above, then you say it. If there's no restriction, then it would look just like the domain. So it always starts, I'm not saying this is always true in all of mathematics, but for us, it always is going to start with x element of the real numbers or y element of the real numbers, yeah.
So will there be a restriction for x?
Well, what do you think? That's a good question. I'm not going to answer it right now. I want you to think about it. Could you make a parabola? With what you know about parabolas so far, could you draw a parabola or make a parabola that the domain won't be x, can be anything? Think about that. I don't want anybody to shout out that answer, but think about it. Okay, let's make a quick note here. So we have this equation, y equals x squared plus k. K is the number that we use in this course. In grade 11, for some reason, they'll change it. Like y equals mx plus b is always y equals mx plus b. But for some reason, this isn't. Like some textbooks use q, some use k. In grade 11, they call it c probably, but there are other things. So it's not standardized for some reason. So there's nothing necessarily magic, but for us, we're going to use k.
Is K being constant?
Doesn't really stand for anything. Because there's going to be a whole bunch of kind of constants. So we can't just use k. Okay. So this is what we say. K is a vertical shift or translation. Two different words mean the same thing, shift and translation. Up or down by the value of k. So see, now I don't need a table of values to tell me what that does to the graph. I know that when it says plus 5 outside like that, I just move everything up 5. From the base graph, y equals x squared. So you got to know the base graph, and then from there I move everything up 5. Yep. Yeah. Okay, and then let's look at an example. So if I have y equals x squared minus 5, in all of the practice over the next few days, and then again, this gets revisited, like I said, in grade 11 and grade 12, we do this thing where we describe the transformations. So this is what we're learning, is we take that base graph, or the parent graph, y equals x squared, and we transform it. We apply transformations to it. And that changes what it looks like. And we can make any parabola in the world with that. Okay? And so what we do is we describe the transformations using proper terminology. That's what this means. So this has a vertical shift down 5. I said 4 important things there. Which type, or like, is it vertical or is it horizontal? You have to say that. If you just said shift, I know you say down, but we want the word horizontal or vertical in there. Okay. I said shift, so what happened there? So that's the type of transformation. I said down, so the direction, I didn't say -5, I said the word down. So again, we're doing this sort of with words, and then by how much. So you need all 4 of those things in this case. And what if it was y equals x squared plus 7? That would be obviously a vertical shift up 7. So again, I say all 4 of those things. That's when you're asked to describe the transformations using proper terminology. Everybody good so far? All right, what's different about this one? This one's x minus h in brackets, all squared. So we just learned what k does. Now we're going to find out what h does. And then we're done for the day. So we're going to start with our first one. And even though we're doing a table of values, that's not what we're practicing. That's why I'm kind of just giving you the values. So again, hopefully, maybe by now you know these. You can just figure them out yourself, right? 9, 4, 1, 0, 1, 4, 9. And let's graph those. That's our base graph. Okay, so we need different x values for this one. This is not something you need to know how to do, so don't be confused by it. We're going to start at 2, 3, 4, 5, 6, 7, and 8. This is just part of the lesson. You don't need to know how to find those numbers. Okay, because we're not doing a table of values. Okay, 2 minus 5 is negative 3. Negative 3 squared is 9. 3 minus 5 is negative 2. Negative 2 all squared is 4. 4 minus 5 is 1. Negative 1. Negative 1 all squared is 1. 5 minus 5, 0. 6 minus 5, 1 squared. 7 minus 5, 2 squared. 8 minus 5, 3 squared. Now you maybe can see why we picked those numbers. But again, that's not something you need to know how to do. I'm going to keep saying that because I really want you to understand. No table of values. Okay, so let's graph them. 2 and 9. 3 and 4. 4 and 1. 5 and 0. 6, 7, 8. If you take a moment and think about it, okay, while you're popping that down, it's not the same as linear relations. You can't just use negative 3, negative 2, negative 1, 0, 1, and 2 all the time. If I tried to use that for that second one we just did, it wouldn't even look like a parabola. You wouldn't really see the shape of it at all. So it's another reason why a table of values just will not work for this. Whoops, yeah, y equals x minus 5 all squared. Okay, one more, and then we're going to chat about what happened. So this one should start at negative 6, whoops, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, and 0. Negative 6 plus 3. Negative 3 squared, 9. Negative 5 plus 3 is negative 2. Squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 0 plus 3 is 3. 3 squared is 9. Negative 6 and 9. Negative 5 and 4. Negative 4 and 1. Ooh, that wasn't very good. All right, call that guy 3. There's a couple of things to notice here, similar to what we did, but there is an important little twist. Jaden, what did you notice? Or were you going to ask something?
Yeah.
Yep.
Do the arrows always have to go past the graph?
No, they don't. But they need to be past that last set of points. What do you notice? What do you think? Anybody? Ziggy?
So when it's like plus 3 and the vertex is like 3 back and the x back.
Okay, so when we did plus 3, the vertex moves to the left. What would you have expected it to do? Like, what would be your guess? What would have been your guess?
Move to the right.
Move to the right. When we did the vertical stuff and we added 3, we went up 3. That makes sense with how we view the number line. When we subtracted 4, we went down 4. That also makes sense. In this case, I added 3, but I went into the negatives 3. And when I subtracted 5, I went into the positives 5. So it has the opposite effect. That's something you absolutely need to know. Okay? That's not a mistake. That's not an accident. That's how it works. But the nice thing is, in grade 10 and grade 11 and grade 12, whenever you have something in brackets like that with the x, that's always how it works. It always has the opposite effect that you would expect. So it's kind of an easy thing. You get used to it. You might not remember it at first, but you get used to it as long as you are kind of working with this and reflecting on whether you're getting them right and wrong and that kind of thing. So when I look inside the bracket and I see a -5, I automatically know that's going to take my graph and move it right 5. What moved right? Everything. Every one of those points, it did not change the shape. They all moved to the right all together. So I'm going to put this back to 0. So take a look. There's my graph. And if I take h and I move it to the right 5, notice that it's x minus 5 squared, and every point moved to the right 5. Like this point came from here. It moved over 5. This point came from here. It moved over 5. The vertex came from there. It moved over 5. And if I go the other direction, 3, it does the same thing. It takes all the points and moves them over 3. What did I want for? Moves them over 3. Okay, and what if I did both? So every point, this point here moved over 3 and down 4. But it didn't change the shape. So as long as you know the base shape of a parabola, that red curve there that you're looking at, what it starts looking like, and you understand that the number in the brackets moves it horizontally, and then the number outside the brackets moves it vertically, you don't need a table of values. You just start with this, and you move every point to where it needs to go to its new destination. Okay, so that's how we're graphing, not with the table of values. Okay, let's take a look at this. So the domain for x squared is still x is an element of the real numbers. Did it change for any of those? Megan? No. Very good. How about the range? Okay, so we already did this for the last one. So it's y is an element of the real numbers such that y is greater than or equal to 0. Did it change? Riley? It did not change because we moved side to side. We moved horizontally. So for both of those, it didn't change. The vertex did change. It starts at 0, 0. It's a really important thing to know that the base function, the vertex is at 0, 0. When I had a -5 in the brackets, where did it move to? So the x moved to 5, but the y didn't change. So it has the opposite sign from what's in the bracket. And in this one, it was a +3, so it moved to the left 3 to -3, but the y did not change. Axis of symmetry. Well, that's based off the x value of the vertex, so it's x equals 0 here. What is it in the next one? If I look back, well, it's x equals 5, right? The last one, x equals -3. And the optimal value, that's based off the y value of the vertex and the range, so that part did not change. Minimum of 0, minimum of 0, minimum of 0. And again, as we said, thinking about how it changes those properties or not and how it changes the graph or not is how you're going to make the connections that you need to make. Okay, so y equals x minus h squared. H is a horizontal. Shift, or remember translation is the other word you can use. Left or right by the value of h, and special note, opposite direction than what you might expect. So for example, y equals bracket x minus 6 squared is a horizontal shift to the right. It says minus 6, so you would think it goes to the left, but it doesn't. So it goes to the right 6. Notice how I said all four things again? Y equals x plus 2 squared is a horizontal shift left 2. Any questions about that? When you get that written down, I want you to put your pencil down, sit back and relax. Take a deep breath, but focus and watch what we're doing, because what I'm about to do next is very important, but you're not going to do it with me. You're just going to watch me do it, because then you're going to go home and practice it. Okay? So I'm going to graph this without a table of values. Okay? How do I do that? So for your homework tonight, when you're practicing, every one of these graphs, at least at the start, you're going to draw the base function or the parent function. So I know that the parent function has a vertex at 0, 0, and it goes over 1 and up 1, and it goes over 2, up 4, because it's just y equals x squared, and it goes over 3, up 9, because 3 squared is 9, and negative 3 squared is 9, right? So there's my parent function. That's not this. That's not y equals x minus 4 all squared minus 5. That's y equals x squared. Now, what does the negative 4 do? Liam. Moves me to the right. How much? So I take my vertex and I move to the right 4. Well, what about the negative 5? What does that do? Jaden.
Shifts it vertically
Down 5, so I should actually have my point there, not up here. There's my vertex. What about this point? It moves over 4 and down 5. Whoops, I went too many. What about this point? Over 4, 1, 2, 3, 4, down 5. Notice how the growth pattern hasn't changed. So I can use that. So from my vertex, I can go over 2. What is it going to do? It's going to go up 4. Over 3, what's it going to do? Up 9. So 5, 6, 7, 8, 9. No table of values. Do you agree that I did not use a table of values to graph that? I used the transformations. I used my understanding. X minus 4 all squared minus 5. That blue curve is what I was supposed to draw. I started with the red one so I could compare, and I moved every one of those points over 4, down 5, over 4, down, 4, down 5, over 4, down 5, over 4, down 5. Right? All together. Or I thought about moving the vertex and using the growth pattern to find more. So now, what if I wanted to state all of that important details? So it's positive 4, negative 5. Look at how that's related to the equation. The vertex is in the equation. You see that? What's the domain? X is an element of the real numbers. What's the range? Y is an element of the real numbers such that y is greater than or equal to negative 5. What's the axis of symmetry? X equals 4. It has a minimum of -5. The x-intercepts aren't clear, but I could guess what they are. You know, that's not something that is super important that we guess x-intercepts. We'll look at calculating them later. The y-intercept, if I want one more step, I could figure it out. What else? What are we missing? Anything else that we should mention? Yeah? Optimal value, I got minimum, but direction of opening, it opens up. Oh, and the growth pattern. So it goes over 1, up 1, over 2, up 4, over 3, up 9. Any questions?